All right, there's a truss, a roof truss on the top of this building here. That's a truss up there. What we're going to do now is we're going to start taking this stuff we've learned about equilibrium, and we're going to start applying it to a couple different cases. One is trusses, which are used in different situations. You still see a lot of roof trusses that are used on buildings. This one's more for show, I think. I'm sure it serves some structural features, but I think it's also to kind of for show there on the outside of that building. Back in the day, they used trusses to build bridges. You can kind of see back there, there's a truss bridge. That's a railroad bridge crossing the Willamette. This one's kind of interesting because as you get closer to the camera, you get into more and more modern forms of bridges. A lot of the old Willamette bridges are truss bridges too. The old one in Albany, the old one in Corvallis, those are truss bridges, okay? From there, they went to these big steel girder bridges with a little bit of bow in them to kind of help them support the span there. And from there, they went to this precast concrete style of bridge. So they kind of, as you get closer to the camera, you get into more and more modern styles. Okay. I don't know what's going on with that bridge in Corvallis. I know that is kind of a choke point for traffic going out of town. It's just one lane. I don't think, I don't know if there's any talk of replacing that or not. I'm not sure. It would certainly free up traffic. What's that?
It's like historic or whatever.
The train, the historic, the truss one's the train.
Okay.
It's like
that's right.
like
okay.
Track.
Yeah, right.
I don't know if they still use it.
You know the truss one used to actually turn sideways so that those would get through?
Okay.
Really?
Yeah, bridges they're tricky. Yeah.
The whole gear underneath one of the piles.
All right, now what we got with trusses is we take long, thin, what we call members, and we join them into triangles. That's what gives trusses stability. So by definition, trusses are joined into triangular kind of what I call panels. So there's a triangle, there's a triangle, there's a triangle. And these triangles are stable. They don't move around. Okay, they're long, thin, what we call members too, long beams. Not really beams because beams are horizontal, which is why they use a different word for it, okay? There's a truss on campus, that's the greenhouse. Very simple little structure there, but it uses triangular panels. Okay, that's a truss type construction there for that. Okay, so trusses, and I'm on page 480 now, or when you take these long, thin members and join them into triangles, they're assumed to be joined only at their ends. We assume that they're joined with frictionless pin joints, which is a bit of an assumption. We also assume that the loads are only applied at the joints. Okay? And maybe I need to add that to my little spiel here. So the loads are assumed to be applied at the joints. The joints are where the members come together. Okay. As a result of all this, each member is considered to be what's called a two-force member. So the member is either all in tension or all in compression. So tension pulls on joints, compression pushes on joints. So when we do a truss analysis, what we do is we walk through the truss and analyze each member as a force, find the internal force, and then work through to the next joint and keep working your way through to figure out all the forces in the members. Once you know the forces in the members, you can design them to resist those forces. So truss analysis involves working through a truss and finding the forces in the members. They're either tension or compression, one or the other. Okay, a two-force member, which I'll abbreviate T2FM, is an object that has two pin joint supports and has forces applied only at the joints. So that's a two-force member right there. Okay, these struts that hold up the roof at the Salem Convention Center are two-force members. You can see the pin joints right there. Okay. There's a railroad bridge over the Santiam River at Jefferson. Okay, if you look on there, that's probably the light just wasn't right for this photo. But you can see it right there. See that pin going through there? Hard to see. Got a better picture. Here we go. It's a little bit better up top. See that pin up there? They actually used to use actual pins in these big pins. Okay. So that's the assumption, is that's a frictionless pin joint. Here's the greenhouse. See that? Those are pin joints, aren't they? They're real simple little pin joints, but that's what they are. They flattened out that tube, drill a hole in it. You can put a bolt through it and bracket it to the support below. That's a pin joint. Now the large trusses that use I-beams and things like that, they are not usually pin jointed. Now sometimes they were riveted, but quite often they use what we call a gusset plate. A gusset plate is kind of like, it's a plate of steel that has rivets through it or bolts that hold those members together. Now that isn't a true pin joint. There's a better picture of a gusset plate right there. You can see all those rivets in there holding those members in. However, here's some gusset plates there. Okay. Here's plates that are used for this connection. You can see them there, okay? I don't know what they call them. Anybody build roof trusses? They've got those kind of plywood plates with spikes in them that they use at the joints. I don't know what those are called. Is there a name for those? Anybody know? Or I'm not sure, but they're like gusset plates. Now, those aren't true pin joints, but they act like pin joints. If that member is long enough, if you have it sticking out a long ways like these truss members do, and if you apply a force perpendicular to the member, you're going to rock it a little bit. For the small amounts of deflection, they do act a good bit like pin joints. Now, it's not perfect, but it's a pretty good way to model them. And of course, always remember that when I'm doing engineering analysis, I'm modeling stuff. It isn't the perfect truth of what's happening. I'm making a model. So I model that as a pin joint. And when I analyze it, I'll get a pretty good approximation of the forces in the members. Okay? So there's just a whole number of examples of how these joints are pin joints. Okay? Here they actually built it that way. That allowed them to make those members thin and slender, which is what they wanted for the architectural appearance of them. Okay? Here they actually did put pins in there, as you can see. Here they put bolts through. That is a pin joint. Those gusset plates aren't quite, but they function a good bit like it when you think about how that load would affect that long, thin member there. Okay. All right, now, on its own, a two-force member can only support an axial load, a load that goes from one pin to the other. So on its own, all a two-force member can do is support a load that is directed from one pin to the other. It can support that load. But if the load doesn't go from one pin to the other, one two-force member can't do much with that because this thing will just start to rotate like that, won't it? Okay. Now, you might say, well, just to prevent that, what am I going to do? What I'm going to do is put a second two-force member in there to prevent it from rotating. So now I can support that vertical load. But the way I'm doing it is this is pushing up, and that's pushing up, and that joint is in equilibrium. One two-force member can't support a non-collinear load that goes from joint to joint, but two can. Okay. So that's why you're building these triangular panels, to get the multi-forces coming into those joints and keeping them in equilibrium. That's the idea. Okay. Okay, now two-force members on their own can only support an axial force. For that reason, if you look at the action and reaction on the members, they're either in compression, where they're being pushed on, or they're in tension, where they're being pulled, one or the other. Okay. So these are free body diagrams of the members. They're being crushed, pushed in, compression, or pulled, tension, one or the other. See, they don't get those perpendicular shear forces, which simplifies the design of them. Okay. That's why we want them to be two-force members, so we don't have to deal with shear forces in them, which are perpendicular to the axis of the member. Okay. All right, so what we're going to do here is called the method of joints. All right, so we're going to try and find the forces in the members of the truss. Now, here's how I remember this. I'm going to analyze the joints, and I've got a little phrase up there that I use to help me remember this. Members in tension pull on the joints because I'm analyzing the joints. Members in compression push on the joints. So you have to remember that what these arrows signify is not what's happening to the members, they signify what the members do to the joints. So these are pulling on those joints. This member is in tension. The one on the top is pushing on the joints, so it's in compression. So those arrows indicate what happens to the joints. Okay. So my goal here when I analyze a truss is to figure out the forces in the members. So the first thing I do is find the reactions. That's pretty good advice. We want to find the reactions on the truss supports before we begin our analysis. Okay. So let's look at how we would solve out a truss using the method of joints. I'm on page 490 is where I'm at. So here I have a truss. So I got 1, 2, 2, 1, 6 meter span. So roughly 20-foot span. And I've got this truss built. It's about 1.5 meters high, so that's maybe 5 feet high. So 5 feet high, 20 feet wide, 20-foot span. All right, now what I do, I've got the loads applied. I've got these forces applied, 8,000 and 7,400. I've got reactions at A and F. Okay, before I start here, I want to do a couple of things. I want to do the trig, and I want to find the angles of the members. I usually use arctangent for that. So I got 1.5 to 1 for this one and that one. So 1.5 to 1. 1.5 to 1. Do the trig on that, I get 56.3 degrees. For the other one, what have I got? I got 1.5 to 2 for those. Do the trig, I get 36.87 degrees. Okay. Now, before I jump in and try and solve out a truss, I want to find the reactions on the entire truss. So what I'm doing there is I'm treating the truss as it's one solid object. Okay, that's my next thing to do. So I'm treating it like it's that. And I just solve for the reactions. So I've got 8,000 newtons times 1 meter, negative because it's clockwise. I've got 7,400 newtons times 1, 1, and 2, 5 meters, clockwise. I've got the 9,000 newtons there times 2 and 1 makes 3 meters, negative because so it's clockwise. And then pushing back, I've got the sum of the dimensions, which is 6, if you can still see it here. I know I'm putting a lot of marks on this thing, but 1, 2, 2 and 1 makes 6 times RF. I can solve for RF, it's 12,000 newtons. All right, then I can solve, so that gets me this one here, and then I can go sum of Fy and set that equal to 0. I got RAY up, I got 8,000, 9,000, 7,400 down, so RAY is 12,400 newtons. And then I got no forces in the X, so RAX at that pin joint is 0. I'm assuming F is a roller there, so no X reaction there. Okay. So I do that stuff before I jump into these trusses. I get the angles in the truss, and I find the reactions. Unless I have a very good reason not to, I always find that stuff first. Then I'm ready to jump into the truss and solve it out. Now, the way I do that is I look at it and I want to start at a place where I have a known force and no more than 2 unknown members. So I'm going to try and find a joint with a known force and no more than 2 unknown members. So let's kind of have a look here. Does B look very good? 1, 2, 3 members, not too good. How about E? Not too good. Boy, I'm not doing too well here so far. How about D? Oh my gosh, that's 5 of those. That's not too good. All right, but how about A and B? Would those work? A and F, I'm sorry, would those work? I think they would, okay? Two unknowns. So I can go ahead and start at either A and F. I think I started at F. So let's have a look at F, and let's look at the systematic way we would do this. Okay, I'm going to start at joint F. My goal here is after I found the reactions and the angles, I want to find all the forces in all the members. So here's how I do that. I'm going to cut a free body diagram out like that. So I've got DF and EF, and I've got that reaction of 12,000. Okay? So what I'm going to do is cut that free body diagram out. The members that I cut through become forces. That's what happens when I cut through something. So those are now forces. I know the way they act because they're two force members. The line of the force follows the line of the member generally. It goes from joint to joint. DF is horizontal. EF makes a 56.31 degree angle with the horizontal. So now I've got a little free body diagram I can work with. Okay. So here's my free body diagram right there. Now, when I look at that, I'm going to start trying to come up with a nice, easy way to approach the analysis. I want to keep the work on me to a minimum. I want one equation and one unknown if I can possibly do that. All right. So I'll look at some of fx, and when I do that, I get two unknowns, don't I? Because I've got two of those members that go in the x direction. I've got FEF, and I've got FDF. So I don't think I want to start with sum of fx. How about sum of fy equals 0? That might be a better bet, okay, because all I've got is one unknown in the y direction, FEF. So if I start with sum of forces in the y direction, I can solve for FEF, okay? We're doing all right with that? Okay. So sum of Fy is 0, 12,000 up. As I have assumed coming down, I've got the unknown FEF with a 56.31 degree angle. I want the y component of that, which is opposite the angle, and I will actually apply it in its proper place at F. So that y component coming down will be sine 56.31 times FEF. Okay. I'll take this term to the other side of the equation. Sine of 56.31 is 0.8321. FEF, that'll become positive because I've taken it to this side of the equation, and I solve for FEF. 14,422. Positive answer. Positive answer means my assumption was correct. It does act down and to the right, so that means it's pushing on the joint, which means it's in compression. There we go, 14,422. That is the force in EF, compression. We good with that? Okay. Once I've got that, now I know FEF. Now I can go sum of FX and set that equal to 0. I got FDF. I have assumed it to be acting to the right, so that gets a positive. I got plus cosine now because I want the adjacent side. For EF, I want this side, adjacent to the angle, times the 14,422. Solve out FDF, I get negative 8,000. Now the negative means I assumed incorrectly. It doesn't act to the right, it acts to the left. If it acts to the left, it's pulling on F, so it's tension. Okay. Y'all okay with that? Okay. So now I've found two of them. right, now what this does is once you get two of them, which you should get when you do your first joint, I like to mark up the truss. And I put the arrows on to show what the members do to the joints. So they're going to look like that. DF pulls, EF pushes on the joints. Now I can go to another joint and solve it out. Okay. Now I got a couple options. I can go to D or E. Where do you suppose you'd go next? What's the best one to go to? I think E. And you're counting up the unknowns? Yeah, I think so. So we got two unknowns at E. I got 1, 2, 3, 4 at D. I can't go to D yet. I got too many unknowns. So I'll take it up to E. And I'll do the exact same thing again. With the exact same level of excitement here, what we've got is we've got all those forces acting at E. Okay, I've got FCE and FDE as unknowns. I've got the 14,422 and the 7,400 as knowns. I got to remember to pick up that applied force up there. Okay, that one. Sum of Fy is 0, negative 7,400 plus sine 56.31 times the 14,422, then minus sine 36.87, because I'm after the opposite sides here is what I'm after, so I'm using the sine function. FDE. Solve for FDE. It comes out positive, meaning it does as I assume pull. It pulls on E down and to the left. Once I've got that, I can go sum of Fx, set that equal to 0. I'll get FCE as an unknown, minus cosine 36.87 times 7667 for FDE, because I'm using the adjacent side, so I'm getting this one. I've got minus the other one. These both act to the left. They're both adjacent, so they're both cosines. Cosine 56.31 times 14,422. Solve for FCE. I get 14,133. Positive, meaning it does indeed do what I assumed, which is push on the joint, so it's compression. Okay? That's basically how you work through a truss. You find the angles and reactions. You start at a place that has a force and no more than two unknowns, and you start working your way through joint to joint, step by step. Okay. We'll cover more of that on Friday. Yeah, question there.
Is it, I guess, what's the situation where forces on D and E aren't symmetrical?
If they have different angles, or if there's other applied forces that throw them out of balance.
Okay.
Is that good?
Yeah.
Okay. So, yeah, we do want to be a little careful. I don't make a lot of assumptions for the trusses. I just work through them, and they kind of work out to be what they work out to be. All right. They're not. Sometimes they're not as symmetrical as they might appear. So let's do a few more of these equilibrium problems because they're a lot of fun, and we want to do those. So let's have a look. Let's do 274, 5, and 6. And these will be due on Monday. Right. And that will be the 24th, I think. All right, so we'll call it good.